Hello, everyone. Welcome to Temporal Graph Reading Group. Today, we are very glad to host Wanyu Zhao and Charith Mendis, who will be presenting their recent work on TGOpt and TGLite. So I will start with the speaker introduction. So Charith Mendis is an associate professor at the University of Illinois at Urbana-Champaign. Previously, he was a visiting faculty researcher at Google and was instrumental in designing and developing the TPU cost model used in production. His research interests are in automating compiler construction and in building high-performance ML systems. He received his PhD and master's from MIT and his bachelor's from University of Moratuwa. And he recently co-led the DARPA ISET study on the ML optimized compilers for heterogeneous architectures. He is also the recipient of the DNSF Career Award and numerous other awards. And Wanyu Zhao is a first-year PhD student in computer science, also at the University of Illinois, Urbana-Champaign, and under the supervision of Charith. And their current research focus on developing efficient and scalable systems of temporal graph learning, and with a strong interest in the intersection of systems and machine learning. So I will hand the mic to you for the presentation.
Okay,
and
cool.
Thanks for coming for the talk today.
Yeah, thanks a lot, Andy. So I'm gonna start presentation now. Is everything work? Can you hear my voice and see my screen?
Yes, we can hear you well
okay.
and can see the slides. Yeah.
Yeah, okay, cool. Okay, today I'm going to present our work on optimizing TGN training and inference. And I'm doing this talk on behalf of Yufeng Wang, who's a prior master in our group under the supervision of Charith Mendis as well. And I'm going to talk about two works. One is TGOpt, redundancy-aware optimization for TGAT model, and another is TGLite framework. So today's outline will be some background knowledge about temporal graph neural network training and inference. And next, I'm going to proceed to our two works. TGOpt is our redundancy-aware optimizations for one TGN model inference, and TGLite framework is our framework built for TGN models. And after that, I'm going to show a demo to show how to use our TGLite framework. Okay, so our world is composed of entities that interact and form relationships with each other. This makes a graph an important data representation, where entities are represented as nodes and their interactions are represented as edges. Compared to regular graphs with a static set of nodes and edges, temporal graphs are dynamic and changes over time. For example, you might have new users in social networks. Here, new links created through time and new users are added to new social networks. And also, you may also have new transactions in a financial graph and evolving facts in knowledge graphs, etc. These temporal graphs can be represented in two different ways. One is discrete time graphs, where we take a snapshot of the graph at certain intervals. The other is continuous type graphs, where we have a stream of graph changes, such as adding new edges or adding new nodes. Here, each snapshot is essentially a static graph, so it captures very little time information. how much information you capture depends on how large the time interval is. For example, if this time interval is quite large and you take snapshot with a quite large time interval and the last time information you are capturing through this discrete time graphs. Whereas continuous time graphs have richer time information with these explicit timestamps captured in those models. And time information can be very crucial for certain applications. So we are more interested in these continuous time graphs. Okay, this is about temporal graph, and now a little more about graph neural networks. Here is how GNNs are typically utilized to perform representation learning. So we have a graph as input and output node embeddings for nodes in this graph. Specifically, the input includes graph structures, node features, and edge features, and we pass these data to GNN models and get the representations or embeddings for graph nodes. What a single GNN layer does to compute targets representations is to encode and pass the neighbors information to the targets, which is referred as message passing or message flow. Computation-wise, it will perform a segmented sum on the neighbor representations to get the target representations. So here for each node, each line can be the representation of their neighbor, and it reduced to their representations here. After we get node embeddings, we can pass them to another model. For example, an MLP classifier to classify the nodes, or predict the existence of a link, which can also be a MLP classifier to classify if there's a link or there isn't a link. So now we have an idea of static GNNs. Let's talk about temporal GNNs. In temporal GNNs, new edges are created through time. For example, here, an edge is created at time t6, and next, two edges are created at time 7. Input is typically a continuous time graph with a list of temporal edges as the graph structure. And the output becomes the temporal embeddings for graph nodes. And this introduction of temporal information complicates TGN models by extending each targets with the timestamps. Here, it also extends to timestamps. So instead of computing some embeddings given a node index, we need to compute temporal embeddings, which is now represented as a node index paired with different timestamps. What's more, instead of simple sampling to get neighbors, we do temporal sampling, which only consider past neighbors to avoid using future information. And unique modules have been devised to account for temporal information like time encoder and node memory, etc. Here are two TGNN models performing different applications like user item interaction prediction and future twist prediction. Across these different applications, temporal GNNs have shown superior performance over classical static GNNs like GAT and GraphSage. However, to efficiently utilize these temporal graph neural network models, there remains challenges. First is TGNs are computationally more expensive with the introduction of temporal dimension. As discussed in the previous slide, we need to learn temporal representations instead of one representation without considering any temporal information. And we need to perform some operations unique to temporal graph neural network models. For example, temporal sampling, and it needs to only consider those neighbors who have been appeared before the current timestamps. And also these unique modules specific to temporal GNN models. In addition, TGN's unique data structures and computation patterns also cause call for first-class programming support to both ease the implementation for machine learning people or TGN practitioners and facilitate optimizations. So optimizations are important to increase end user productivity, and comes to our two work on solving these challenges. TGOpt accelerates TGN inference by optimizing redundancies, including deduplication, memoization, and pre-computation. It achieves around 5 times speed up on CPU and around 3 times speed up on GPU for TGAT inference. Here, TGAT is one of the TGN models. And TGLite offers first-class support for programming continuous time TGN models with our main data structure called T-block and some operators on it to operate optimizations on it, and our built-in optimizations that are ready for users to use with few lines of code. We also incorporate the optimizations proposed in TGOpt, and it achieves speed ups 3 times for training and 4 times for inference. To understand our optimizations and the framework better, here's more background on how temporal graph neural networks works. The input is the edge list. The edges appears in different time. So here is the edge list. Each edge can be a triple with source node ID, destination node ID, and the time step. The output is the temporal embeddings. TGN models works by jointly learning on the graph structure and time information. And like study ones I've introduced several slides ago before, the common way to do this is through message passing to learn this temporal embeddings. For this message passing, there are 2 main steps to it. So first, we look at our neighbors and pick out the ones that have a timestamp less than some time t. So here we are going to compute a representation or embedding for this blue node. And first we sample its neighbor as this green node, and next we sample the green node's neighbors, 3 purple nodes. And here we set the time t to be like, for example, 2 hops. And then we'll collect node and time data for each neighbor, aggregate them in some way. So here the information from purple nodes goes to the green node and then goes to the blue node. So we pass these information along all the way back to the starting node to get the representation of the target node. This aggregation over neighbors can be done either with a summation or taking the average, or sometimes more complex like self-attention from transformers. Here, let's look at a model called TGAT. Here's what its aggregation network looks like. So it first sample some recent neighbors and get these features for each node and the time encodings of based on the difference from the target node and the timestamp of the edges. And then it aggregates node and time delta information. Here we get using self-attention from transformers. And here the neighbors are from a neighborhood we sampled through here. And next, we'll compute the final embeddings based on the representation of the node we get here and concatenate with its node features as well. So here we do this a couple of times and study multiple layer TGAT model layers. We analyzed this computation of TGAN model. We found that the main computation in most GN models is aggregating information from neighboring nodes. And on top of this TGAT tends to use an expensive attention mechanism here, along with some other time encoding operations here to capture the temporal nature of the neighborhood. And in fact, as we will see later in our results, these two kinds of operations can take up a very large portion of the total inference runtime for datasets we studied. Here's the dataset is Jody last FM, and these can be as much as 80%, the self-attention mechanism and temporal encoding. Here okay. So with this in mind, we propose TGOpt, which is semantic preserving optimizations exploiting temporal redundancies. Our goal is to improve and accelerate the inference performance. We do this by eliminating redundancies, particularly particularly the redundancies that occur over time. And in doing so, we were able to get significant speedups on both CPUs and GPUs. Specifically, we apply 3 key optimizations. The central theme here is to reduce the amount of work we have with this deduplication and reuse values as much as possible, use memoization and pre-computation. Let's take a look at our first optimization, deduplication. Our observation here is that processing the batch of edges, this can result in computing duplicate embeddings. Suppose we have this example here. There are 2 edges, one edge is with node A and node C, another edge with node B and node C. And both of these 2 edges have the same timestamp T here. With that, we will then process a batch with these 2 edges, AC at time T and BC at time T. When we consider both source node and destination node, this will result in a duplicate target. So we extract the target nodes from these 2 edges. We have AT, CT, BT, and CT. So CT is duplicated here. To see how much duplication exists in practice, we studied several datasets and found that there can be quite a lot of duplications, especially in layer 1. Most of the time, the duplication portion is larger than 50%. So our conclusion here is that a lot of duplicates can occur in a batch, since these nodes can share these edges can share these nodes can share common neighbors, and this target node is duplicated in the batch.
Just a quick question.
Okay.
So here, are you assuming the edges in the batch have the same timestamp, or are you looking at the exact timestamp of the edges?
Exact timestamp of the edges. So if these 2 have different timestamps, then CT here is not the same, and we are not going to compute the same temporal embeddings because we are compute temporal embeddings here. So if this T is different, then we need to compute different embeddings because the sampling neighbor can be different. So if that happens, these are not duplicated and won't be filtered out in our framework. And the data here shows exactly the same temporal node. How many temporal nodes are duplicated exactly. And these can come from sharing a common neighbor at some same timestamp. Yeah.
Right. So my question is basically, because you are not assuming the edges in the batch have the same timestamp, but you're looking at the exact timestamp. So actually, the percentage of duplication you have is independent of the batch size that you pick. Because even if you put all the edges in one batch, it doesn't matter because you check for their inherent timestamp instead of assuming that edges in the batch.
Oh yeah. We don't. Yeah. Exactly. Yeah, that's right.
Okay, so that's just a quick clarification because you mentioned the batch of 200 edges, but actually it doesn't depend on the number of edges you put in a batch.
Oh, yeah. That's right.
Okay,
Yeah. Thank you.
thanks.
So our conclusion here is that a lot of duplicates can occur in a batch, since nodes can share the common neighbors. And a simple way to address this is to add a pre-processing step to filter down to only the unique targets from the batch temporal nodes. If we take our previous example, we have these 3 temporal nodes to compute embedding for. First, we'll filter out to get these unique targets. We also have our inverse indexed in order to map the unique targets back to the original batch to be utilized for the downstream tasks. So we run the computations only for the unique targets, which is 3 temporal nodes here. And then we take the inverse index to produce the final output. This is to preserve the output semantics and the expected output tensor shape. Okay, this is our first optimization deduplication. And now moving on to our second optimization, memoization. Another key observation is that over time, the model can generate the same embeddings. So not just within the batches, but also across time. This stems from our intuition that even though the graph is changing, not everything or not every node is changing all at the same time. So we first take a look at this example. Say we want embedding for node V at time t4 when aggregating from neighbors. The TGAT model does not use all the neighbors, but rather a subset of them. We specifically look at a strategy called most recent neighbor sampling. If we sample for 2 neighbors, we'll get these 2 nodes here, assuming that T1 is less than T2 and less than T3. So T2 and T3 is the most 2 recent neighbors for this node at time T4. And even if there are new neighbors, but it appears at a larger time step, so we do not consider it to be the candidates of the sample neighborhood for this temporal node at T4. So this means that whenever we sample for the same node at the same time, we should always get this neighborhood. And we will always aggregate from this same subgraph. Okay, now let's say we extend this example to sampling 3 neighbors. Each of the neighbors can further sample their neighbors, and we'll get some subgraphs for those. Now, assuming node V has a new edge with a new neighbor D at time T5, if we sample for a different time, here is T6, we'll get a different subgraph. So this for the neighbors of node V at time T4, we have these 3 nodes, A, B, and C. And now, because we have a different time T6 here, which is larger than T4, larger than T5 and T4. And we'll get a different neighbors here is B, C, D. However, we also notice that some old neighbors are retained as well. So here, node A is evicted, and node D is introduced, but B and C are still in each neighborhood at the same time. So most recent sampling will help give us the same subgraphs, at least for these subgraphs. So with the same subgraphs, it implies that we will do the same computations here and here and get the same embeddings for this BC and this BC. So we should be able to reuse the embeddings we have previously computed. Again, this is for inference optimizations. So the model is not changing. So with the same node ID and timestamp, each embeddings should be the same. So we should be able to reuse the embeddings we have previously computed here instead of doing it again. To see if we can take advantage of this, we look at some data sets where we track the individual embeddings that get generated and whether they can be reused as the blue line shown here, or if they need to be computed as the orange line shown here. So from this plot, we can see that there are a lot of embeddings that we can reuse. And if we zoom into the first few days as the graph evolves, there are already a lot of embeddings we can reuse. A simple technique to exploit this is just to memorize those embeddings and memorize and cache those embeddings in the earlier iterations during training and reuse them in the later stages of training instead of recomputing them. We start by constructing the output tensor of the expected shape. So each entry is for one temporal node. And before doing any computations, we first go look for embeddings we can reuse in the cache table and copy those into the output. So these green entries are the ones we can find in this lookup table. We just copy them to here. And for any misses, we will then run the original computations and fill these blue entries. And then we'll store those into our cache as well for the later usage. And here is our memorization or cache strategy to reduce the computation during inference. And let's come to our last optimization, pre-computation. Our observation here is related to time encodings. For this, we return to these two equations here. We see that the first phi function is always computing on a constant 0 because we are computing the time delta on the target node and its attached edge. So the timestamps for that node and the edge is the same. And for the second phi function, it's not immediately obvious that when we are looking at this, but if we look at this execution over time, we see that the input time delta values are often clustered around 0. This is because since we are doing most recent neighbor sampling, the time differences between the target node and the edges will tend to be very small. A simple optimization we can do here to leverage this is to take a slice of the time window starting at 0 and pre-compute the time vectors. So we can reuse them during inference. And this is our optimization of pre-computation for the time delta encodings. These are the three redundancy-based optimizations we have: deduplication, pre-computation, and cache memorization. And reviewing the whole picture on TGAT and plus our TGOpt optimization, we can do duplication to the batched temporal nodes to filter to the unique nodes and reduce the computation, the amount of computation we need to perform to compute those temporal embeddings. And for pre-computation optimization, we will pre-compute the time encodings and based on the observations that the time delta often cluster around time 0. And for cache optimizations, we will cache those temporal embeddings we compute in the earlier stages of inference and reuse those for embeddings instead of recompute them each time. So that wraps up our optimizations. Now we'll look at some our results. One of our main results is that for this inference runtime, which is measured as the total time to work through all the batches. So here, lower is the better. And the numbers on the bars is our speed up against the baseline. On CPU, we see significant speed up against the baseline across the board. In particular, we see that the speed up for the Jody dataset are noticeably higher than the other dataset at 5 to 6 times speed up. And as for GPU, we get very good speed up as well at around 2 to 3 times. Okay, so this is our TG optimizations, particularly for TGAT model inference. And we generalize these optimizations to both training and inference in our TGLite framework. And we are also looking at more models. Our TGLite framework is lightweight programming framework for continuous time temporal graph neural networks with key designs as with the key designs of data objects and compute operators. So I'm gonna continue introducing our framework, TGLite. Again, we will use TGAT model for a case study and see how to implement a TGN model. The first step is to sample recent temporal neighbors, and next encode neighbor add time deltas into time features, aggregate node features and time features using self-attention, and to get and repeat that for a total of L layers and get the final embeddings. Let's look at how to implement in code. So if we examine the one reference implementation done in plain Python and PyTorch, what you will see is that first we need a way to represent the graph. Here's the node IDs, node timestamps, and the edge indexes, and sample neighbors here. So we'll have these very ad hoc data structures and utilities. Then you'll notice that because we have to do this message passing over multiple layers, that ends up being a kind of tricky recursive implementation here. So here we call time conv for one layer's message passing, and it will recursively call this function. And these are the TG optimizations I introduced, how to implement our TG optimizations in this plain Python and PyTorch. So we can see these optimizations is beneficial to TGNs, and we can just implement those here as some duplicate invert, because we need to invert it back to the original tensor shape. And we can also do cache lookup here. But a problem is that those optimizations require pre and post processing step. So now our main logic is sandwiched between these steps, and the programmer has to manage all of the bookkeeping. Not to mention that an efficient implementation will mean going down to the C++ and the systems level. And researchers might not have the knowledge or time for doing this. So perhaps using a framework will help us to do that. These are popular frameworks for static graphs. In particular, in DGL, there are message flow graphs. These message flow graph objects can be used to represent a set of nodes and their sample neighbors. So this is nice that it turns the recursive flow into an iterative one that's easier to reason about. However, the programmers still need to implement all the time-related time-related pieces themselves, since there's no first class part. And when we survey prior work that supports temporal graphs, there are ones like this dyno graphs that has nice optimizations for discrete time graphs. And another one is the only one we are aware of that supports continuous time graph is this TGL. Unfortunately, it doesn't expose any sort of programming interface and lacks optimizations. So it'll be difficult for users to explore new model designs or implement more efficient ones. So this is how TGL works. So it configure the models, samplings, and hyperparameters through a YML file, and their model definitions like this. They have different blocks to control what kind of techniques to be utilized for node memory and what techniques to be utilized for the main aggregation architecture. And it's very hard for users to define their own models directly on top of this or implement any optimizations. So here at a high level, let's take a look at our TGLite library. So the the programmer imports our library. Our framework works with PyTorch, so users can leverage all the things they like in PyTorch to start their implementations. Then for the actual computations, they will use our abstractions and operators to construct those flows. Here we have the T context to control the runtime behavior, like optimizations for TGN models. And dedupe is one of the optimizations we provide in the framework to do deduplication optimizations. And you can just enable it with just this one line code. Let's revisit the TGAT example. So if we implement this using TGLite, then we get access to a library with things tailored to temporal graphs, such as this T graph object for storing training data and this T sampler for sampling recent numbers. We get to use what we call T blocks in an iterative manner. And we can operate on those T blocks using built-in operators, such as sampling and aggregating from neighbors. Lastly, applying optimizations is as simple as adding 1 or 2 lines of code. This T block abstraction is at the heart of our framework, and it enables defining many different operations and optimizations. So a T block essentially captures one hop dependencies between the set of target nodes and that we are working with and their temporal neighbors. So for static graphs, we have these MFG objects, message flow graphs. And now for temporal graphs, we have T block objects with first class support for time-related attributes and operations. If we zoom in a T block, it'll look something like this. And there are 3 key distinguishing factors about T blocks. First, we can construct a doubly linked list out of the T blocks. This allows us to explicitly capture multi-hop relationships that are often seen with TGN models. And second, we can incrementally build and manipulate the mapping of the nodes to their neighbors. And lastly, T blocks have a hook mechanism for registering arbitrary functions to run later, which comes in handy for scheduling post-pre-processing steps. Now let's see how these design choices help with defining both computation and optimization operators. One common thing we want to do is multi-hop aggregation. So we have this aggregate operator. This is sort of a higher order operation that takes a function and applies it to multiple blocks. Internally, it traverses the doubly linked list of T blocks using attributes like previous and next, and apply that function, aggregation function like attention layer. For optimizations, we have a preload operator that efficiently prefetches feature data using pin memory. It will simply traverse the doubly linked list of T blocks. And lastly, redundancy-based optimizations such as deduplication is another operator in our framework. So to explain this one, let's take a look at an example again. Suppose we have 3 target nodes here and their corresponding timestamps. So we can sample for their neighbors. We see that the 3rd target here is duplicate. So we'll end up sampling the same neighbors, and we'll perform the same, computations for this one. So instead, we can do is filter out the duplicate targets and then perform the computations as usual. And then do the filtering by duplicating duplicating the outputs. In this way, we are semantically doing the same thing and getting the same results, but doing less work. So for this, dedupe operator, it will manipulate the mapping of the T block in place, and it takes advantage of the hooks mechanism to register the post-processing step. For training, we measure the average epoch running time, so lower is better. We show the results for 2 datasets here, and more can be found in the paper. We see that across the board, TGLite is able to either match or outperform the other framework. And a big part of that is that we are able to take advantage of the redundancy-based optimizations. And here the figure is all training feature data resetting on GPU device. And next is training data reset on CPU host, and we need to fetch the feature data from CPU host to GPU side. And for this case is very important to optimize for data movement, and which we do in TGLite, and that brings the speed up to at least 3 times. And the user can tap into this by simply using the preload operator. Next, for inference, we show results for the other 2 datasets as relative runtime speed up. So higher is better. Here we achieve even better speed ups of 3 to 4, from 1 to 4 times over the respective TGL baseline. To get some more insight into this, we conducted an ablation study on the redundancy-based optimizations by applying these optimizations once a time. Before applying any of them, we see that there's a bit of overhead, which we found is due to external kernel library calls. But we also have speed ups thanks to the preload operator. With the optimizations, we see that we can get much better speed ups, with duplication and caching being the better ones, as they help minimize on expensive calculations like self-attention. One thing to note is that these optimizations are semantic preserving, so the accuracy of the models are retained. Lastly, we also experimented using larger scale datasets. For instance, GDelt has 191 million temporal edges, which is order of magnitude larger than the other 4 standard datasets I showed in the previous slide. On the A100 GPU, we are able to achieve much higher speed up with 6 times and 9 times, showing that our optimizations have a bigger effect as the dataset grows. And on the older V100 GPU, TGL actually runs out of memory, while TGLite is able to keep a low memory footprint and finish training without any issue. Okay, so to wrap things up, we've introduced a framework with first-class support for continuous TGN models, which is centered around our T-block abstraction, and our experiments show that we can achieve significant speed ups for both training and inference with some of the optimizations we proposed in TGLite. And TGLite is open source, and we welcome the community to give it a try. And here's the QR code to our code and our documentation. Okay, so I'm gonna finish the presentation and show a demo here. Do we have any questions so far?
So some
Yeah.
clarification, so I guess, so for the T
Okay.
block you were talking about, so
Okay.
what happens when your one hop neighbor, because you have a lot of like repeating edges in temporal graphs. So
Yeah.
what happens when a connection have multiple timestamps associated to it? So this source and destination have, let's say, 10 timestamps. So which block or hop do you consider that to be?
So each T block captures one hop relationship. So this target nodes will created through the batched edges, and we sample these targets after duplication. We'll sample these target nodes neighbors, and these neighbors are saved here in the first T block. And next, we will use these source nodes as the target nodes of the next T blocks, because they are right now the target nodes we are going to sample from. And it will create the next T block. And another structure like this appear shows up.
So
Does that
so
answer
my
your
question
question?
is more, how do you handle the multiple timestamps? So if you have in the first hop neighborhood, because here you're looking at it as a flattened out like a static graph with the timestamp as the edge attribute, right? So what happens when you have a source an A and B, and between A and B there's three different timestamps? Do you just keep the most recent one and throw out the other two, or what do
No,
you do
yeah,
with the three timestamp? I'm
yeah.
still a little
Here,
bit
here,
confused.
yeah. So
But
here,
can you zoom in on the?
yeah. Oh, sure. So here you can consider the target nodes as a pair instead of just one single node ID. And all the target nodes are saved here. For example, A at T1 and A at T2 and A at T4, T3. These
Okay.
different temporal nodes will be saved all inside the T blocks as the target nodes we are going to compute embeddings for. So unless it's exactly the same, or else we will save all those target nodes here in one T block. So it can be multiple entries for the same node ID, but
Oh, I see.
they need to be
Okay.
attached with different timestamps. Yeah.
Okay. Thanks. There's also a question from the audience.
Oh, okay.
Do you want
Yeah.
to just unmute yourself, Shabazz?
Yeah.
Oh.
First of all, congratulations for this work. I think it serves as an important step towards like standardization of frameworks for temporal graph neural networks, and with this like impressive improvement in the time performance, it's really going to be helpful for the community. But my question is,
Yeah. Thanks.
have you done any like space complexity about this? Because like you have a lot of data sets have a lot of edges, and you're doing a lot of memoization. You're seeing time encoding with respect to nodes. So like, does this time improvement come at a significant cost of requirement of a higher memory requirement?
Yeah, it has some overhead. For example, to cache those embeddings, we need the cache tables. Let me find the slide here. Yeah, so we need to have this cache tables here. And in our framework, we set a limit to this cache table size. So the default, I can show it later. We normally set the cache table size to be limited to millions of edges, which is quite small, because the cache table is stored in CPU memory set, and we'll check the embedded cache in CPU side first, and move those heated ones to GPU for usage. and it's not very large overhead, I would say. For example, if you consider one embeddings to have float point single float point numbers, and there are 2 million such numbers, then that would be 2 megabytes. So it's not very large overhead, and it's quite fast to look up because we implemented with C++.
All right.
And
So
OpenMP, yeah.
So like not everything that has occurred is like cached, right? Like you still caching something.
No. Yeah, no, we don't cache all the. There's a chance that the computed embeddings are evicted as if it exceed the cache size.
Oh, thanks.
Okay. Okay, cool. So I'll proceed to the our demo. So here's how to define a TGAN model and run TGAN model with our TGLite framework. So let me start with, so here is to import, the first step is to import the libraries. So the TGLite is dependent on Torch, so we need to import Torch first, and next import our TGLite. I'm gonna run this here. And next we can define TGAN model. So we utilize the modules provided by Torch. And we have some neural network defined already in the library, TGLite library. So we'll import the temporal attention layer here. And as normally what you do in deep learning model definition, we'll define the temporal layer, the modules here in it. What's different here is that we pass the context, which is of type TG.T context, which controls some runtime behavior, like do we need to do you want the optimizations, or do you need to create a faster data structure like TCSR that will help sampling. So after defining these model lists, we can define our forward here. So the batch size are represented with this T batch, and this T batch will create a T block. And for the number of layers, we iteratively create a T block, which is done by sample to generate the source nodes from the target nodes. And we do some optimizations on top of it, like deduplicate, because I've shown in the slide that they are duplicated target nodes. So we'll deduplicate them. And also we'll find that we'll cache the embeddings, and next we will do the sampling, and it generates the T block in an iterative way. And with this preload operator, we'll preload the feature data from CPU memory to GPU memory, or just get the feature data from if you decide to store all the feature data in GPU side, and this will fetch or retrieve those feature data that will be used and put them in a way that are ready for computation. And this is for loading the first embeddings, because in the first layer, the embeddings is just the feature data. And then we do this aggregate. And here the aggregation function is the self-attention layer. And we, with this T-batch function split data, we can split the data to source node, destination node, and the negative nodes, and we can compute the scores and return the scores. This is how we define a forward function for this TGAN model. Let me run this. So after we've defined the TGAN model, we can control some of the hyperparameters here, like learning rate, dropout, Here we set a number of layers as 2 and number of heads as 2 for our attention layer. And the number of neighbors to sample is 20. And the sampling strategy is most recent sampling. And here we use a small data set wiki because it only takes several seconds to run. And we set the X number to be 3 to see the result quickly. And here's how the configurations to control whether to enable the optimizations. So let's disable all the optimizations for now and see the result. Okay, so here's some setup, just like normally done in DDL training, set the seed and the device to compute on, and load data. And create a T sampler for efficient sampling. And here we create model, loss function, and optimizer. And now we are ready for training, and just run it.
So since we are waiting, just to mention that
Okay.
we are at the end of the hour for the reading group. So if you have like other meetings, feel free to jump out. But I think we can wrap up the demo here and the questions.
Okay, finished. So the average time is, so the total time per app running time is 16 seconds, 17 seconds, 16 seconds here. Yeah, and this one is without any optimizations. And now we are going to enable all the optimizations and run it today. Yeah, so here we can see that per app hook runtime reduced to less than 10 seconds. Yeah, cool. So this test is on I'll say the smallest data set we have to show a fast result, and the optimizations is even better for the larger size data set. Yeah, so that's it. Do we have any questions regarding how to use TGLite?
Yeah, so thanks for sharing the demo, and it looks very easy to use. And thanks for sharing the very interesting work. And also, I think this is very important work, since the neighbor sampling can be used in any future like architecture, and it's a very fundamental part of doing temporal graph learning. So yeah, so thanks for the presentation. And if you want to share of these demos or like more links, just send to me and I can like put them on the website for everybody to see as well.
Okay.
And
yeah. Okay,
and
so so this is in our the website of our documentation, and the demo I showed is this one. So it's the demo I showed. So welcome to try and use it. Yeah.
Okay, sounds good. I have a final question. Because I think the actual limitations for current temporal GNNs, like the training is slow, but actually the problem is when you want to do proper evaluation for them, because the existing evaluations in the original TGAP paper and so on, they sample one negative sample per positive edge, which is makes it have extremely high scores on the evaluation. So the bottleneck is usually when they are sampling a lot of queries for evaluation, like you want to compute something like an MR or something on large data set. where you need to construct the neighbor embeddings, like the node embedding for a particular timestamp for thousands of nodes at once, because you want to query all the source and destinations. So that's where I think most of the methods are the slowest. So so potentially there are more optimizations to see how you can optimize the inference further, especially if you assume you need to compute a lot of queries at a single timestamp. So then many of the duplicates that you mentioned can be collapsed even further.
Yeah.
In some way.
We tried to use TG benchmark temporal TGB, and we saw that you have more negative samples, not just one for one edge. Instead, you have a lot of negative samples that are more difficult to compute on, which calibrates the evaluation or validation. And we also find that time can be very, very, very long. Yeah.
Yeah. So, yeah. So definitely a lot of very interesting future work. And thanks so much for the presentation. And glad to have you at a reading group. Yeah. So thanks everyone, and we can wrap up here for this week. And yeah, see you all at the future reading group. And let's thank the speaker again for the nice presentation.
Okay, thank you, Andy.
Thank you very much.
Thank you.
You.
Bye.
Bye.
Bye.